So in free response problem 4, it's asking you to find if the series converges, and if it does, find the exact sum. So we are given the summation from n equals 3 to infinity of natural log of 1 minus 1 over n squared. So it's important to note that if it wants us to find the exact sum, there are only two series that we can do this with, telescoping and geometric. Now I do not see any n powers in here, so I'm going to assume that this series is probably telescoping. So we need to figure out a way to break it down into two terms if we're going to use telescoping. Well, I have a natural log of 1 minus 1 over n squared, so let's see if we can start there and try to break it down. So I end up getting summation from n equals 3 to infinity. Now I have a 1 minus 1 over n squared. I can get this to a common denominator, so let's start there. I have natural log of n squared minus 1 over n squared. So all I did was this becomes n squared over n squared minus 1 over n squared becomes the new term inside. Now, I can break this up a little bit further. N squared minus 1 has two roots, so I'm going to go ahead and I'm just going to rewrite that really quickly. N equals 3 to infinity, natural log n minus 1, n plus 1 over n squared. Okay, so now we have two different terms, and from here we could use the rules of natural logs to break them up right away. However, what I'm going to do is I'm going to do a little more algebra inside, because again, I only want two terms in my telescoping series. If I have multiple terms, it can be a little hard to keep track of everything. So let's see if we can condense these terms down and get them into two terms. So I have summation n equals 3 to infinity, natural log of, so I have an n minus 1 and an n plus 1, and then I have an n squared on the bottom. So technically, I can group one of these n terms with each one of these. So I'll have n minus 1 times n plus 1 over n. Okay, so now I have two terms inside of the natural log, and all I need to do is use the properties of natural log to be able to split them. So if I go ahead and rewrite out what my final sum will be, my final form will be, I have natural log of n minus 1 over n, and because these are multiplied together, I'm going to add them with two separate natural logs, n plus 1 over n. Natural log of n minus 1 over n plus natural log of n plus 1 over n. Okay, cool. We have our two terms, so now let's go ahead and start expanding out some of them and see if we can get them to cancel out and figure out the sum. So, in this case, if I write out, I start at n equals 3, so if I write out my n equals 3 term, I end up with natural log of 3 minus 2 over 3, 3 minus 1 over 3, so I end up with natural log of 2 over 3, plus natural log, 3 plus 1 is 4 over 3, so 4 over 3. Okay, nothing's canceled so far, but it usually doesn't in the first term, so let's expand out a little bit more. Natural log, when I plug in n equals 4, 4 minus 1 is 3, 3 over 4. And I have plus natural log of 5 over 4. Okay, so I still don't see anything canceling, but I notice that I have natural log of 4 over 3 and natural log of 3 over 4. So those terms are actually very similar, and the reason is because of the rules of natural logs. So when I have natural log of a over b, I can actually write it as negative natural log of b over a. That's just a property of logarithms. So what I'm going to say is I'm going to say that natural log of 4 over 3, natural log of 3 over 4 is actually equal to negative natural log of 4 over 3. And since that's the case, natural log of 4 over 3 minus natural log of 4 over 3, those terms now cancel. So I know that anywhere in here, if I have natural logs that are opposite fractions, I can just cancel them out. So when I do the n equals 5 term, if I expand it out even further, I end up with natural log of 4 over 5. Sorry, this 5 corresponds to the n equals 5 counter. There's a natural log in front, plus natural log, and when I plug in n equals 5, I get 6 over 5. So now I have natural log of 4 over 5 and natural log of 5 over 4. So those terms will cancel because, again, I know that using the properties of logarithms, I can go ahead and cancel those out. So what it looks like is I'm left with one residual term in this case, and it looks like this secondary term for my natural log will always be retained. So I can go ahead and I can write out my partial sum and see what I get. So my partial sum in this case is equal to natural log of 2 over 3, because that's just a residual term, plus natural log, and this term corresponds to natural log of n plus 1 over n, because no matter what n term I write out, I'll always be left with this second term over here. So this becomes n plus 1 over n. Okay, so we found the partial sum, but to find the exact sum and prove convergence, we have to take the limit of the partial sum as n approaches infinity. So s is equal to the limit as n approaches infinity of s sub n, which in this case, when I take the limit of this as n approaches infinity, I end up getting natural log of 2 over 3, because that's just a constant, so that doesn't change. And I have natural log of infinity over infinity, which translates to natural log of 1 when you apply L'Hopital's rule. Natural log of 1 is just 0. So all I end up with for my final sum is that s is equal to natural log of 2 over 3. So therefore, this is a convergent telescoping series, and its final sum is natural log of 2 over 3.
The Teaching Center, UF's Learning Resource Center.